Let's imagine a random experiment where we're performing 5 independent success or fail trials. And so what I mean by that is that we've got 5 independent trials, 1, 2, 3, 4, 5, and in each of those trials, we have 2 possible outcomes. We either succeed, we'll call that S, with probability P, or we fail the trial, fail, F, with probability 1 minus P. And so we can see straight away the probability of succeeding or failing a given trial is going to be P plus 1 minus P is going to be 1, which is what we'd like. But we don't just have one of these trials, we've got 5 of these trials performed consecutively and independently. So if I tell you what the outcome of trial 3 is, you won't be able to make any better a guess of the outcome of trial 1, except that it'll be a success with probability P and a failure with probability 1 minus P. And so let's look at a sample outcome for this experiment. So we could get a success on the first trial, followed by a failure on the second, another failure on the third, a success on the fourth trial, and a failure on the fifth trial. And so this is a sample outcome of this experiment. S, F, F, S, F. And in general, all our outcomes are going to look something like this. And so if we were to define our outcome space, as we can with any experiment, it would be sort of a string together of a bunch of S's and F's. And so if we had 5 consecutive failures, fail, 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 we would represent it by 5 F's. And if we had 4 consecutive failures and then a success, we would represent it by 4 F's and then an S. But we would distinguish between this outcome and the outcome where we got 3 failures, a success, and then another failure. Even though the amount of successes and failures are the same in these 2 outcomes, we want to distinguish between them because the success happened at a different point. And so the outcome space of this experiment would be all these possible strings, all these possible combinations of failures and successes, so long as that there are 5 in total. Okay, so the first thing we want to do is to get our head around what the probability of a given one of these outcomes is. And so let's just try and calculate that. Let's try and calculate the probability of getting 4 failures and then a success. So probability of F, 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 S. Now, what this is the probability of 5 different events occurring. It's the probability that I got a failure on the first trial, and got a failure on the second trial, and got a failure on the third trial, and a failure on the fourth trial, and a success on the fifth trial. But since these are independent events, we can represent this probability simply by the product of the probability of getting the particular outcome at each stage of the experiment. So we could write this as PF, 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 and one more times PF, times the probability of getting a success. Okay. And this is just equal to, well, each of these is equal to 1 minus P, and so this is equal to 1 minus P to the 4. And the probability of success is P, and so we've just got P at the end here. Now let's compare this to the probability of getting this outcome here. The probability of getting F, 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 S, F. And we can see we've got 3 failures, which are independent. So we've got 1 minus P, the probability of getting a single failure, to the power of 3. We've got a success, and then we've got another failure with the probability 1 minus P. But we can just rewrite this to be the same as above. 1 minus P to the power of 4 times P to the power of 1. And we can see that there's a common pattern of kind of occurring here, is the probability of getting a certain combinations of F's and S's. So a probability of getting a particular combination is going to be 1 minus P to the power of the number of failures. And so there's 1, 2, 3, 4 failures in both of these cases, times P to the power of the number of successes. In this case, it's just 1, and so it's just P by itself. And so if I asked you to give me the probability of success, 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 failure, success, you could quickly say there's 1 failure, so I've got probability 1 minus P to the 1, and 4 successes. So I've got a probability times p to the 4. And so this is our probability. Okay, and so we've got our head around the probability of each of the fundamental outcomes of this experiment. And now what we're going to do is define a random variable. So our random variable, we're going to call that x. And we're going to say x is equal to the number of successes. Okay. And so if we asked what we get when we put this outcome into x, we'd say we get 1. So x of FFFFS is 1. And so 2, x of FFFSF is also 1 because we've got just one success. And if we plug this outcome into our random variable x, we'd get 4 because there are 4 successes. And we can sort of grapple around the possible values of x, and we can have no successes, so x could be 0. We can't have a negative number of successes, so x starts at 0. We can have any integer number of successes, 0, 1, 2, 3, 4, up to and including 5 successes. Because we've got 5 trials, we can have 5 successes, so 5 successful trials, but we can't have more than 5 successful trials because we're only running 5 trials. Okay, and so x is going to be somewhere, it's going to be equal to 0 or 1 or 2 or 3 or 4 or 5. And so to really grapple our head around this random variable x, we need to figure out what the probability of getting each of these 6 distinct values is. All right, so the probability, for example, that x equals 1, okay, what's that going to be equal to? Well, remember when we were talking about the probability of each of these distinct outcomes? We said that it really only depends on the number of failures and the number of successes. And so for any outcome, for any sort of string of FFFSF that gives us x equals 1, when we put that outcome into our random variable x, every outcome that maps to 1 will have the same probability. And so we've got 2 example outcomes up here. We've got 2 outcomes where we've got 1 success, FFFFS and FFFSF, and notice they both have the same probability of occurring. And so to find the probability that x equals 1, we just need to figure out the number of outcomes with 1 success and just times that number of outcomes by this probability which we've already derived, which is 1 minus p to the power of 4 times p. And so our next question is, how do we figure out the number of outcomes that had 1 success? And the answer to that question is, how many different ways can I arrange a single success amongst, a total of 5 trials? And because I sit down, we can say, okay, for this single case, it's very obvious. The S can be either in the first, the second, the third, the fourth, or the 5th position. And so there's 5 different ways. There's 5 different ways to choose this single success. And so in this case, we can say, okay, the number of outcomes with 1 success is 5, and we can write the probability that x equals 1 is going to be 5 times 1 minus p to the 4 times p. And that's all well and good for this specific case, x equals 1, but I want to know in general, how many outcomes with here 1, but if x was equal to 2, it would be how many outcomes with 2 successes. I want to know how many outcomes with little x successes are there in general, okay? And so to figure that out, we need to become comfortable with a concept called combinations. I'm going to introduce a new bit of notation, which is called combinations. Combinations. Okay. And I'm going to write it like this. And it goes n. We read this. We've got a set of brackets. In the top, we've got an n. And in the bottom, we've got a k. Okay. And we read this as n choose k. And so what this number represents is if I have n objects, how many different ways can I choose k objects out of those n objects? And we had an example just then with 5 objects. So here n equals 5 and k equals 1. How many ways can I choose 1 object from 5 objects? And in that case, it's very obvious. There's 5 ways that we can choose a single object from a group of 5 objects. But let's suppose we had n equals 5 and k equals 2. How many ways can we choose 2 objects from a list of 5 objects? And it turns out that there's a formula for this, which is n factorial divided by k factorial times n minus k factorial. And just as a refresher, n factorial just equals n times n minus 1 times n minus 2 all the way to 1. Okay. And so, for example, if I've got 5 outcomes, and I want to ask the question, how many ways can I choose two objects from a group of 5 objects? It would be 5 factorial divided by 2 factorial times 5 minus 2, which is 3 factorial. Okay. And this would just be 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 3 times 2 times 1. And we can simplify this. We can see that these cancel out. And we just get 5 times 4 divided by 2, which is just going to be 10. And so there are 10 different ways that we can choose 2 objects from a group of 5 objects. So, now that we have a convenient way to represent the number of outcomes with a certain number of successes, we can write a general formula for this probability that x is equal to a particular value, and we're going to call that value little x. And it's going to be equal to the number of outcomes with little x successes, okay, and that's going to be 5, which is our total number of trials, divided by x, which is the number of successes that we want, okay. And now, notice we've got x successes, and so we're going to have 5 minus x failures, because we either succeed or we fail. And so we can write the probability of a particular outcome where we have little x successes is going to be 1 minus p, the probability of failing to the power of the number of failures that we have, which is going to be 5 minus x, times p to the power of the number of successes that we have, which is x. And notice that we've got a special case of this above. Here, little x equals 1, and so 5 minus x equals 4, and x equals 1. So we've got 1 minus p to the 4 times p. And here, we've replaced our number of outcomes with little x successes with 5 choose x. Okay, and so now, for this particular scenario, where we're doing 5 trials in a row, we've got our heads around the probability that this random variable we defined is going to be equal to a particular value. It's going to be 5 choose x, which we've defined up here, times the probability of failing to the power of the number of failures, times the probability of succeeding to the power of the number of successes. But what if we had not 5 trials, but n trials? Well, in that case, our set of trials would look like this. ... 1, 2, 3, 4, all the way up to n. And an individual outcome would look like success, fail, 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 and there'd be n different successes or failures in a particular outcome. And so now, for this more general case, where we don't have 5 trials, we've got n trials, what's the probability that x, our random variable, which still is the total number of successes, equals to a particular value x? Well, this is still going to be the number of outcomes with x successes. Okay. It's going to be multiply that by the probability of failing times the number of failures we have to have if we've got x successes, which is going to be the total number of trials we have minus the number of successes, so n minus x, multiplied by p, the probability of succeeding, to the power of the number of successes we have, which is little x. And to write this in the notation we've just learned, well, the number of outcomes with x successes is basically saying how many ways can I choose x successes out of n possible trials. And that's going to be n choose x. times 1 minus p to the n minus x times p to the x. When we've got a random variable x that has this probability mass function, where x equals 0, 1, 2, all the way up to n, we say that x is binomially distributed. And so this random variable x, we say x is distributed. We use a little tilde sign there. We write bi to denote that we have got x with a binomial distribution. But the binomial distribution has two inputs here. And the first one is n, the number of trials, and the second one is p, the probability of success. And so, just to finish off, if I told you that we had a random variable y that was binomially distributed with 4 trials and a probability of success of 1/2, you could straight away look up this formula and write out the probability that our random variable y takes on a particular value, little y. And that's going to be 4 choose little y, the number of ways that we can choose y successes from 4 possible successes, multiplied by 1 minus 1/2 to the power of 4n minus y, multiplied by 1/2 to the power of y.